All right, guys, so now we want to cover section 1.6. This is the section on electrical power and electrical energy. Now, electrical power and energy are really related to one another. What I'm going to do is I'm going to peel back to the definition of power. And this actually comes from physics. And in general, the power of a system is the amount of energy either provided by the system or supplied to the system by the time that it takes it to. In other words, in the language of calculus, the power by definition is the time rate of change of the energy, or dw dt. Keep in mind, W here is the work/energy, like so. Now, this power right here, this is general power, right? It could be mechanical power, it could be power of some other sorts, but what we're actually interested in is electrical power. So one of the things that I can actually do to talk about electrical power in the context here is, if I write down my definition of power, by the chain rule, I can rewrite this as dw dq times dq dt, like this. So this is by the chain rule in calculus. It really is almost as if these dq's right here kind of cancel out. They're not actually canceling, but it's as if they were canceling out, and notice in the numerator and denominator you'd have dw dt. So I'm fully justified in rewriting it like this. However, recall that the voltage across 2 points is the work done by unit charge, right? And the current flowing past any point is dq dt. So this power equation at the very top can actually be rewritten as, well, power is dw dq, but that's the voltage, and dq dt, but that's the current. So here, the electrical power of a system is always a product of the voltage times the current. Right. Now, there are some units here associated with electrical power. The unit of electrical power in SI units, here you can actually see it is a joule per second. This is also known as a watt. Right? And in the context of electrical power, this is also a volt times amp. So there are many ways to rewrite this unit of watts. Now, one really important thing that I want to bring your attention to, and this is really kind of all important because in this class, one of the trickiest things to do is really keeping track of signs, whether it be a sign on a voltage, a sign on a current. There are also going to be signs associated with a power. So this equation here that we have, P equals IV, notice that it is an expression that relates the voltage to the current. So the passive sign convention must apply. This is really a very important point here. So you have to be careful and observe and respect the passive sign convention here. That means that the definition of power above that we just ended up deriving using first principles, that's only half of the story. So I really want to go back and take a look very briefly at two separate cases. So suppose that you have in each case an ideal basic circuit element like this. It's a two-terminal device. And for the first element, I say that the voltage looks like this. Same thing for the second one. However, the current for this one goes down this way, while for case number 2, it goes up that way. Now, the power in each instance is actually going to be rewritten as V times I, but again, observing the passive sign convention, remember, whenever the direction of the current is in the direction of the voltage drop, then any relationship that relates to the voltage to the current takes a positive sign. Conversely, if the direction of the current is in the direction of the voltage rise, it takes on a minus sign. So over here, notice that this current, the fact that it is going from essentially the positive here down to the negative, right? So it is going down this way. That means that the sign on this power equation looks like this. It's plus. While over here, notice that this current is beginning at the negative reference point, goes up through the circuit, ends up at the positive. That is going through a voltage rise. That means that by hand, I must add in those signs. So over here, if you're computing electrical power, for case number 1, you use this equation. If you're computing electrical power for the second case, you must use the second equation and you must put in this minus sign by hand. That's extremely important. Right. Now, notice that there are 2 signs that are associated with the power, and there are physical ramifications to this. So I want to talk very briefly about the sign convention for the power. It's more of an interpretation. Now, one very big thing that I want to say here as well is that the sign on the power, whether it be positive or negative, how you interpret what's happening with the element is what happens with the final sign by the end of the calculations. So you never interpret what the sign on the power is based on the equations that I just showed you guys, this one or this one. It is only by the end of the calculation, once you've plugged in values and numbers, that you can interpret whether a element is either consuming power or whether it is actually generating power. So these signs must be interpreted by the end of any calculation. And later on, we'll go through an example to show precisely that. Now, let's go back to the 2 cases. So there is case number 1. If by the end of the calculation, you calculate all of the powers and you find that this is positive, then one of the things that we say is that the power is consumed by the circuit element inside the box. There is a technical name for an element that consumes electrical power. In the nomenclature of electrical engineering, this is what we refer to as a load. The second case is if by the end of the calculation, the power happens to be negative, then the power is generated by the circuit element inside the box. And in the nomenclature and jargon used by electrical engineers, this is known as a source. that'll take care of all of the theory that we need in order to go through a few illustrative examples. I hope you enjoyed this, and we'll see you for the next videos.